Alright, so today we're going to cover graphs of polynomials. Okay, so starting off, we're just going to look at the general form of polynomials. So you have your linear polynomial. And remember, that's just 1 degree. And that has the form of ax plus b, where a and b are constants. Like 3x plus 2, 7x plus 5, something like that. Okay. Then you have your second degree polynomial. Which is your quadratic. That's just ax squared plus bx plus c. Or it could be x plus some number, well, x plus or minus some number. Okay. Or you have your third degree polynomial. Which your largest term is 3. Well, your largest term degree is 3, not free. So ax to the third plus bx squared plus cx plus d. Or you have x plus or minus, instead of question marks, we'll say x1, x plus or minus x2, or x plus or minus, we'll say some x3. Okay, so instead of the question marks, I'll just use x1 and x2 here. Clean up that 2 a little. And it keeps on going on and on and on and on and on until you get to your nth degree polynomial. Bless you. And I'll put that underneath since it's going to get a little bit longer than the other 2. Well, the other 3. And your nth degree polynomial. Here, so you have your third degree, so your highest exponent is 3. For your nth degree, it could be the 6th or 7th or 10th degree, whatever it is. You have your first coefficient times whatever degree your polynomial happens to be. Then you have your other coefficient next to the next smallest exponent, plus your other coefficient next to your next smallest exponent, and that just keeps on going and going and going all the way till you get to some a or x squared, all the way down to your first degree term and all the way down to your constant. Okay, so we know that all of those a's, an minus 1, an minus 2, all the way to a sub 0 are constants. And we know that a sub n is not equal 0. Okay, so that's kind of a general explanation for an nth degree polynomial. Okay, any questions on that so far? Nope, I'll leave that up for a few more seconds. And then we'll talk about power functions. Okay, so now we'll look at power functions. Okay, so power functions are really just functions that are single terms. Okay, so those are single terms. That is the product of a real number a coefficient and a variable raised to a fixed number. Well, a fixed real number to be specific. Oh, don't know why I put a colon there when a period would have been just fine. Okay, so a power function is denoted by, or you can say it's more of the form. So you have f of x equals, let's say, some number k times x to the power of p. K and p are constants. Oh, thank you. Okay, so for example, if you have f of x equals 3x to the fourth power, okay, it's one term. You have the product of a real number, a coefficient, and a variable raised to a real number, well, a fixed real number. So this is a power function. Okay. So same with f of x equals 2 over x to the fifth power. That's a power function because you can rewrite it as 2 times x to the negative 5 power. So as long as you have that real number exponent, it's a power function. Okay. Now if you have something like f of x equals 3 to the power of x, that's not a power function. Because remember, you have to have a variable raised to a real number, not a real number raised to a variable. So this kind of switches it up. So this one would not be a power function. Since you have to a real number raised, a variable raised to a real number. There, switch those around. Get a variable raised to a real number. Okay, and that is the opposite. Oh, move that up a little bit. All right. So any questions on that one? All right, I'll leave that up for a few more seconds. Okay, so we're going to use that to discuss the end behavior of polynomial functions. Okay, now just for a quick identification, polynomials of degree 2 or higher, they will not have any sharp turns or any kind of discontinued points or anything like that. They'll be continuous and they'll actually have curves throughout them. So polynomials of degree 2 or higher do not have sharp corners or breaks in the graph. Okay. So in other words, they're smooth and they're continuous. Smooth, which means no corners, and continuous, which means no breaks. And there you go. Okay, so for example, let's say if you have, well, that should have been a smooth corner there. This graph here. Okay, it's smooth, it's continuous, there are no breaks, there are no sharp corners. So this is a polynomial. Okay. Same thing if you just had a linear graph. Smooth, no breaks, no sharp corners. This is also a polynomial. Okay. But if you had, let's say, absolute value, that wouldn't be a polynomial because you have that sharp corner. Or even if you had a piecewise function that may look like that and then go like that. Okay. These two are not polynomials. They're functions, just not polynomials. Okay. Or even if you had, let's say you had the, let me separate that. If you had the graph, it looks like this, bring that up some. And piecewise function that continued like that. Okay. It's not continuous, so it wouldn't be a polynomial. Okay, so it's not a polynomial because it has breaks, so not continuous. All right, so any questions on that one? All right. And we'll do. And if you remember the degree of a function, you might remember this from, did we go rather than 1,000? Or was it 70? I believe it was 70. Can't remember. It was one of those classes, but in case you didn't go over it, the degree of a function is the sum of the exponents of a term. Okay. Now, the highest degree of a polynomial is the degree of that entire polynomial. Okay, so the highest degree term of a polynomial is its degree. Okay, so for example, let's say if you have f of x equals 3x squared plus 2xy plus 3x y to the third plus 7. Oh, move that up a little bit. Okay. Now we can find the degree of each individual term by adding up the exponents. For this one, you only have one exponent, so this one term is degree 2. Okay. Now this one, x and y, you have two exponents, so x, that's just y to the first power. And y is y, let me make that an actual 1, is y to the first power. So this one term is also degree 2. Okay. Now this term, xy to the third, that's really just x to the first power. So this term is degree 4, because you have 3 plus 1. And this term here is actually degree 0 because you can make it 7 times x to the 0 power, and it would still be 7. So this is degree 0. Okay. Now to find the degree of that entire polynomial, you just pick the highest, which in this case is degree 4. Okay. So since degree 4 is the highest term, this polynomial, I thought I had enough room. I'll just put an abbreviation for polynomial. Is degree 4. Okay, so you don't add them together or anything like that. You just pick whichever term has the highest degree, and that's the degree of the whole thing. Okay. Any questions on that? Yes?
How come the 7 isn't just degree like 1?
Oh, because with 7, let's see, let's put that little side note there. Because if you have 7, that's the same as 7 times x to the 0 power. Yep, so that's your only exponent there. Does that make sense? Okay. So any other questions on this one? All right. I'll leave that up for a few more seconds. So now we're going to look at the endpoints of polynomials. And really the easiest way to figure out or remember the endpoints of a polynomial It's the first, remember, I guess you could say the 4 basic ones. Or I guess you could say 6 basic ones. Well, really it's 3, and then you're just putting a -1 in front of it, and it flips over. So if you remember 3, you can remember all of them. Okay, so if you remember, let's say we have the graph of f of x equals x squared. Okay, remember that just looks like that. So this is f of x equals x squared. Okay, so this is your x-axis, and this is your y-axis, or you can also call it your f of x, since y is equal to f of x. Okay. Now the one thing you notice about the endpoints here is that as x is getting bigger, this is going up and to the right. So f of x is getting bigger as x is getting bigger. So f of x approaches infinity as x approaches infinity. Okay. So that just means that it's going higher and higher up as it's going to the right. Now if you notice your left side, that's going higher and higher up as x is getting smaller and smaller because you're approaching negative infinity. So this side would say the opposite, at least for the x. So this side, f of x, is approaching infinity as x approaches negative infinity. Okay, f of x is still getting bigger and bigger and bigger, but it's just doing it as it's approaching negative infinity. Okay, so let's say we get that very same graph, and I'll put that x, that's your y-axis, or we'll just call it f of x. Let's say we have f of x equals negative x squared. Okay. If you remember, negative x squared just flips it over the x-axis. So that looks something like that. Okay. So we see as x gets bigger and bigger and bigger, this side goes down and to the right. So we know that for this side, f of x approaches negative infinity, because remember, it's just getting smaller and smaller and smaller as x approaches infinity. And as it's going to the left, you notice that your x, as it gets further and further to the left, it's getting smaller and smaller and smaller. It's going further and further down. So the further left it goes, the further towards negative infinity it goes. So for this side, or this endpoint, your f of x approaches negative infinity as x approaches negative infinity. Does that make sense? No. Okay, so let's say, well, actually, you only, for these next two, you only have to remember one of them because it's kind of the same, but I'll just write them both out anyway. Let's say if you have your xy axis, or your x, f of x axis. Okay, so let's say you just have f of x equals x. Okay. Or you can have it as f of x equals x to the first power. Okay. If you notice for this endpoint, as x is getting bigger and bigger and bigger, f of x is getting higher and higher and higher. So for this endpoint, your f of x approaches infinity as your x gets bigger and bigger, or as your x approaches infinity. And for this endpoint, your f of x is getting smaller and smaller and smaller, as your x is getting smaller and smaller and smaller. So for this side, your f of x is actually approaching negative infinity, as your x approaches negative infinity. Okay. So what if we get that same graph and do what we did up here, just multiply by -1? Okay, so if we have, let me see, that's your x, and that's your y, or we'll just call it f of x. And if we have f of x equals, negative x. Okay, so remember, whenever you get a graph and you multiply by -1, you just kind of flip it. So if you flip this one over the x-axis, that means this side goes down here, and this side flips and goes up there. So the graph really just looks like that. When you multiply it by -1. So the whole graph just flipped. Okay. Now if you look at this one, or this endpoint, you notice that as x gets bigger and bigger and bigger, your f of x gets smaller and smaller and smaller. It's going down and to the right. So your f of x approaches negative infinity as your x approaches infinity. Okay. Now with this one, if you notice the endpoint is getting higher and higher and higher as x is getting smaller and smaller and smaller. Okay, so for this endpoint, your f of x is actually getting bigger, or your y value is actually getting bigger as your x is getting smaller. So as x approaches negative infinity. Okay, so one more. Let's say if we have, say we have our xy axis, we have our x, and we have our f of x here. And let's say we want to graph x to the third power. So let me move that over a little bit. F of x equals x to the third power. And x to the third power has a graph that looks somewhat like that. So if you notice with this one, as it gets bigger and bigger and bigger, or as x gets bigger and bigger and bigger, your f of x also gets bigger and bigger. So that means for this endpoint, f of x approaches infinity as x approaches infinity. And for this endpoint here, yep, it would approach negative infinity as f of x approaches negative infinity. So if you notice, both of these have the same endpoint direction. So your f of x approaches negative infinity